So welcome you to this module. In last module, we started studying about asymptotically efficient estimators. The idea was that what is expected from any reasonable estimator is that if I have a lot of information from the population, which is in terms of as the sample size is becoming larger and larger, or the sample size is going to infinity, then my estimator should be close to the estimate g theta in certain sense. And one such stochastic closeness is through the convergence in probability. So I define the concept of a consistent estimator. So we say that estimator delta n is consistent for estimating g theta if delta n converges in probability to g theta. Then of course we did some results based on strong law of large numbers, delta method, and we concluded that the sample mean is always consistent for estimating population mean irrespective of what the parent population is. So now we'll study some more properties of consistent estimators. First thing is consistent estimators may not exist. So to see this, let us look at x1, x2, xn, IID normal theta plus mu and variance sigma square. So here the mean further is a composition of two different means. So for example, if I am considering the height of or the income of Indian males or income of Indian adults, my population may be divided into males having height less than 6 and males having height more than 6. What I am observing is the data. I am not observing the data separately, height less than 6 but this mean theta could be the income of people of height less than 6, mu could be income of the people with height more than 6. The data which I observe is total income of the people. So I cannot estimate theta and mu separately. So theta cannot be estimated consistently. Why the proof is very simple. If delta n is consistent for, suppose delta n is consistent for theta, then because of symmetry, theta plus mu is same as mu plus theta, delta n would also be consistent for mu by symmetry. So what does that mean? This would imply that delta n goes in probability to theta and delta n goes in probability to mu. And you know that through the property of convergence in probability that if xn goes in probability to c and xn also goes in probability to d, then c has to be same as d. So this would imply that theta is equal to mu, but that is not given to you. Theta and mu can take any value in R2. So you get a contradiction. So here what is happening is these parameters are getting mixed up. And such issues are called. So here I say the parameter theta is not identifiable. So I can give a definition of a non-identifiability. So suppose x has distribution function f theta mu, which depends on two parameters. One can talk about identifiability in terms of more than one parameters also. So if there exists pairs, two different pairs, theta 1 mu 1 and theta 2 mu 2, such that theta 1 is not equal to theta 2, but f theta 1 mu 1 is same as f theta 2 mu 2. then my parameter theta is unidentifiable. So what it says is I have two parametric points such that two different parametric points give me the same population, as was happening over here. I have a pair theta mu as 2, 3 and 3, 2. 2 plus 3 same as 3 plus 2. They give rise to the same population, normal 5 sigma square. So in this case, neither theta is estimable, identifiable, nor mu is identifiable. They have got mixed up. I can estimate here theta plus mu, but I cannot estimate theta and mu separately because of identifiability issues. So what we conclude is unidentifiable parameters cannot be estimated consistently. Unidentifiable parameters cannot be estimated consistently. Now, consistency says that delta n is close to g theta. Now note that if delta n is close to g theta, or delta n is consistent for g theta, and if a n is any sequence which is going to 1, then a n delta n is also consistent for g theta because of properties of convergence in probability. So in particular, if delta n is consistent for g theta, n upon n plus 1 delta n is also consistent for g theta. In fact, anything going to 1 is consistent for g theta. So what it means is class of consistent estimators is rich. And what it says is, it only says that delta n minus g theta goes in probability to 0. But what I am interested in is at what rate it is going to 0. For example, you know that 1 upon n and 1 upon n square both go to 0. But 1 upon n square goes to 0 much faster. So similarly over here, if you have two consistent estimators, what I know is they are both going to 0. So it would be of interest to know which one is going much faster to 0. Because the one which is going to much faster to 0 would be preferable, because its error rate would be going to 0 much faster, or as a consequence, you would require much smaller sample size to be close to g theta by the same quantity as the other estimator would be. So that way, the order at which this error goes to 0 in probability is of importance, and that can be used to compare different estimators asymptotically. So note that generally for consistent estimators I have seen a sufficient condition for consistency is that expected value of norm of delta n minus g theta whole square goes to 0. If that is happening, then estimator delta n is consistent. Converse may not be true, because you may have delta n consistent for g theta, but expected value of norm of delta n minus g theta whole square may not even exist. But generally, if there is no problem of existence of movements, in most situations of practical importance, for consistent estimators, expected value of modulus of delta n minus g theta whole square also goes to 0. Or if I say it in other words, for any reasonable estimator, you would expect expected value of norm of delta n minus j theta also whole square goes to 0. So for any reasonable estimator in particular for consistent estimator, limit n going to infinity of r delta and theta, which is limit n going to infinity of expected value of norm of this is 0. So that means the average distance between delta n and g theta goes to 0 as sample size becomes very large. Now the same issues over here arises over here. There may be more than one estimators for which this is going to 0. So the issue arises then, I would look for estimator where this expected value goes to 0 at a much faster rate. So if I am giving two estimators, for one estimator this goes to 0 at much faster rate compared to the other. So I'll prefer the one for which it goes to 0 at a much faster rate. So two approaches. So one can compare the performance of estimators through the rate at which the risk is going to 0, or the rate at which this convergence in probability to 0 is happening. As I said, convergence in probability can be studied also through convergence in distribution. So the two approaches to compare estimators asymptotically. Asymptotically means as n goes to infinity. The first approach we call as a limiting risk approach. Which basically talks about this limit and estimator going to 0 at a much faster rate is preferred. Other could be in terms of convergence in probability, or in general in terms of convergence in distribution. Because convergence in the distribution, if the converging random variable is degenerate, that amounts to convergence in distribution. So second is limiting distribution approach. So what I am going to do is I am going to study these one by one. So first let us study this limiting risk approach. So to see that, note that if I have any reasonable estimator, so first is limiting risk approach. So what I have is, we know that I would expect minimally from any reasonable estimator is its risk is 0 in limit. Now, as I said, I would like to see at what rate it is going to 0. To see at what rate going to 0, what I do? I try to multiply it by some factor of n. For example, 1 upon n square. 1 upon n square, if I multiply it by n, still it goes to 0. But if you multiply 1 by n, it doesn't go to 0. So what I do is I define, so let Kn be a sequence of real numbers. So I define r delta n star theta as Kn times r delta n theta. So I multiplied by this Kn. Now let's consider two extreme situations. One extreme situation could be that Kn is going to infinity, and Kn is going to infinity at a much faster rate than n, or sufficiently faster rate. such that kn times 0 or kn times this quantity does not go to 0. It just explodes. Kn goes to infinity. The other extreme case could be situation where kn is, for example, bounded and kn times this goes to 0, which of course would happen when kn is bounded. So two extreme cases are kn bounded What happens in this case? If kn is bounded, r delta n theta is going to 0. This is bounded, so kn times r delta n theta would also go to 0. So this doesn't help, because still, as long as if I take bounded, still it has the same rate. The second situation is kn goes to infinitely sufficiently faster, and in this case what may happen is limit n going to infinity may become infinite. Just multiplying it by kn, although it is going to 0, but once you move and you multiply by kn, that may explode. For example, 1 upon root n. 1 upon root n goes to 0, but the moment you multiply it by n, that goes to infinity, n into 1 by root n. So these are the two extreme situations. One is kn is bounded, it is just lying very calm because kn is bounded. In that case, still if you multiply r delta n by kn, still the limit is 0. The other is I use extreme case that kn goes to infinity very fast. Then this may go to infinite. So this suggests that there may be some intermediate sequence kn such that limit n going to infinity kn is a finite quantity, which is different from 0. So there may exist intermediate sequence kn, and what kind of a sequence is this? This is neither bounded nor it is going to infinity at a very fast rate. So there may exist intermediate sequence kn such that limit n going to infinity of r delta n theta is some quantity tau square which is between 0 to infinity. So that means this is neither 0 nor infinity. Note that it will, this quantity, because it is expected value square, so it is always going to be greater than 0, greater than or equal to 0. So what I am saying, it is tau square, it is neither 0 nor infinity. Now if such a thing happens, that means limit n going to infinity kn r delta n theta goes to a finite quantity, I say that risk of delta n converges to 0 at the rate 1 upon kn. So I say that r delta n theta converges to 0 at rate 1 by kn. So what I do is for each sequence I determine what are their rates, and the one for which this rate is better, I prefer that estimator. So that could be one criteria. Now note that rate is not unique. Note error rate, you can call it a rate or error rate, is not unique. First of all, if kn is an error rate, 1 upon kn is an error rate, 1 upon ckn is also an error rate, because if this is going to 0, c times that would, if this is going to a quantity different from 0 and infinity, and c is any real number different from 0 and infinity, then c times this would also go to some quantity which is between 0 and infinity. In fact, if Kn prime, if delta n has error rate Kn and Kn prime by Kn goes to some constant c, which is between 0 to infinity, then Kn prime is also an error rate. That is clear from here, because if Kn times R delta n going to theta, what I can do is I can define Kn by Kn prime multiplied by Kn prime. Kn upon Kn prime is going to C. So I see with Kn prime. So Kn prime, when I write down Kn prime, I can multiply and divide it by Kn. So it will be Kn prime by Kn into Kn times R delta n theta. Kn times R delta n theta goes to 0, and Kn prime by Kn goes to C. So that would also go to 0. So it would also have rate Kn prime. So it is not uniquely. So whenever I am comparing two different rates, I have to compare those rates in asymptotic sense. So that means if I have two rates, Kn prime and Kn, and if Kn prime by Kn goes to C, I would say that the corresponding estimators are equally efficient. However, if Kn prime by Kn is going to 0, so one has a rate 1 upon Kn, one has a rate 1 upon Kn prime, but Kn prime by Kn goes to 0. Kn prime by Kn goes to 0, that means suggests that Kn is going to infinity at a much faster rate. Or in other words, 1 upon Kn is going to 0 at a much faster rate. So in that case, the estimator for which error rate is 1 upon Kn, that would be preferable than the estimator for which error rate is 1 upon Kn prime. So this suggests that error rate can be used to compare different estimators. Now, let me give a definition of unbiased in limit. Delta n is any sequence of estimator is said to be the unbiased in limit for estimating g theta if the bias or expected value of delta nx is same as g theta. We also say that, so normally what would happen is when we deal with the consistent estimators and if its expected value exists, normally for consistent estimators, it is unbiased in limit as well as the risk goes to 0. Normally, for consistent estimator, delta n, the following two things automatically happen. Delta n is always unbiased, unbiased at least in limit, and limit n going to infinity of R delta n theta is always 0 for every theta. So these are the properties which would normally be satisfied by any consistent estimator theta. So in such a sense, if this thing is happening, then the limiting variance would also be 0. Limiting variance is same as R delta n theta. Why? Because mean squared error, which is a risk, is same as variance plus bias. Bias is 0, going to 0. So that means in limit, variance would be same as the risk. So whether you have a limiting variance approach or limiting risk approach, they are same. So that would be the scenario in most of the situations, because in most of the situations, the estimators which you will be considering, for example, consistent estimators, would be unbiased in limit, as well as their risk would be going to 0 as n goes to infinity. So whether you study their limiting risk approach or limiting variance approach, the two are going to give you the same result. Now, let me give a definition. So you have a delta n. This is a sequence of estimators for g theta. Kn is sequence of real numbers such that Kn goes to infinity and limit n going to infinity of r delta n theta, r star delta n theta, which is limit n going to infinity of Kn times r delta n theta. So that means I have chosen Kn so that Kn times r delta n theta. So this is an intermediate sequence which goes to a quantity tau square, which is between 0 to infinity. Then tau square is called the limiting risk of the estimator delta n. So first of all, note that if I have to compare two different estimators, I try to see what are their rates. I would prefer one for which the rate is going to 0 at much faster rate. Now, if the rates are same, then certainly one can consider what is their limiting risk, because there may be two estimators for which the rate Kn is same. Then I study what is their limiting risk. So as I said before, normally this limiting risk would be same as the limiting variance, because in most situations, any reasonable estimator would be unbiased in limit, and its variance would be going to 0. Now, let me just make small observations over. So suppose delta n has rate 1 by Kn. So that means Kn times r delta n theta is going to a quantity which is different from 0. And Kn prime goes to infinity more slowly or more faster than Kn. What does that mean? That is equivalent to saying that Kn prime by Kn goes to 0 in the case where Kn prime is going to infinity at a smaller rate. When it is going at a faster rate than Kn, then Kn prime by Kn would go to infinity. Then what would happen? Then limit n going to infinity of Kn prime r delta n theta would be either 0 or infinite, because this would be same as Kn times r delta n theta and Kn prime by Kn. So in the first case it would be 0 times tau square. Second case it would be infinite times tau square infinite. So this would be 0 or infinite. So that is why if you have two different sequences at a different rates and one goes to infinity much faster or much slower than the other, then this quantity is going to be 0 or infinite. So in that sense, studying the rate makes sense. So I should try to look at the rate at which the risk is going to 0. So let me do just one definition which is motivated by all this discussion on rate of convergence, that how should I compare two different estimators in terms of their rate of convergence. So that is what the next definition says. So let me write down this definition. So I have two sequence of estimators, delta n1 and delta n2. These are two sequence of estimators for g theta. Suppose there exists alpha greater than 0. Suppose there exists a sequence alpha greater than 0, and a sequence n prime may depend on n, such that n prime goes to infinity as n goes to infinity. So what I try to do is I try to determine the rates of the two different estimators. So such that it happens that limit n going to infinity of n to power alpha delta r delta n1 theta. So this is tau square, so that means its rate is 1 upon n to power alpha. I try to see, now over here is I want to make the same rate n to power alpha. What should be the sample size required over here? So for delta n2, so r delta n prime 2 theta. This is same quantity, tau square. Of course, tau square may belong to 0 to infinity for every theta. So what it says is, I know that delta n1 in limit multiplied by n to power alpha is tau square theta. So this ensures that delta n1 has rate 1 upon n to power alpha. Now I try to see over here what should be the sample size n prime over here, and what is the factor I should multiply over here, so that I get the rate as tau square by theta. Then the limiting risk efficiency of delta n1 relative to delta n2 is defined by limit n going to infinity. So note that to achieve the same limiting risk, when I have fixed the rate is fixed n to power alpha, this would require a sample size of n prime. Delta 2 will require a sample size of n prime. So I say whichever the estimator which requires larger sample size to achieve the same limiting risk should be less favorable, or in other words, an estimator which would be requiring a smaller sample size to achieve the same limiting risk should be preferable. Now here limiting risk I have fixed at tau square by theta, rate is fixed at n to power alpha, and then I see what is the sample sizes required by the two samples. This requires n prime, this is n. So efficiency of delta 1 related to delta 2, so efficiency of delta 1 would be larger if the sample size required by the second one is larger. That means the sample size required by delta 2 is larger. So that means n prime is larger. So this I defined as limit n going to infinity of n prime n by n, provided the limit exists. And is independent of particular sequence n prime chosen. So now I'm in a position to compare two estimators asymptotically, and everything is motivated through the rate of convergence. So two things came on the way. One thing is, first of all, about any estimator I can talk about the rate at which it goes to 0. Estimator for which the risk is going to 0 as a faster rate would be preferable. But then there is a possibility that you might have many estimators which are going to 0 at the same rate. Then what you do is you talk about in terms of a limiting risk. So among all such estimators, the one having the smaller limiting risk should be preferred. And that is what exactly you did over here. Two estimators n to power alpha should have a same limiting risk, n to power alpha. So n to power alpha is the best rate I suppose I can achieve. If you can achieve a better estimator, then all the such estimators would be neglected because they are going to 0 at a much slower rate. So suppose this n to power alpha is the best rate I can achieve. Once that have happened, I know that this is non-negotiable. Then I look for all the estimators for which this happens, then the one for which the sample size required is smaller to achieve the same limiting risk would be preferred. So let me just stop it over here. So tomorrow I'll continue my discussion over here. I'll give you some examples to show how to determine the relative risk efficiency or local limiting risk efficiency. I'll do then a result using which you can directly find out the limiting risk efficiency. So let me stop for today over here. I'll continue from here in the next lecture. Thank you very much.